Hello folks, this tutorial involves with an object impacting a plate, and I'm doing it in the 3D Experience platform with the ABAQUS Simulia solver as the main FEA module in it. Now, I've done problems like this before, but I was assuming that the material, the plate, for example, behaves uh, plastically, but it doesn't damage it. Okay, so in this particular tutorial, I'm going to show you how to model a plate that is subject to damage. In other words, the object destroys a piece of it and pierces through the plate. Uh, the way I do these things is intended for people who are either new to the 3D Experience platform or already ABAQUS users, but they're planning either to transition to 3D Experience or be able to run the software on this platform. This is why the problems that I pick are taken from YouTube channels where a particular problem has actually already been done with the ABAQUS CAE, with all the steps described to you. And I replicate those steps because the interface in the 3D experience of the ABAQUS program is completely different. Okay, so that is the reason behind doing these tutorials. Now remember, I'm not doing anything about the accuracy. I'm not claiming making any claims about the validity of the assumptions that were made in those YouTube channels. It's just that I'm replicating steps. Okay, so this problem that I'm doing is described here. So we have a plate, which is the preface is uh, clamped, and it's being impacted by a cylindrical object, and it just goes through it after it destroys a particular area using a failure damage model. And this particular problem was taken out of that reference where things are all done in the ABAQUS CAE. Okay, so here's the situation. There is an initial gap of 2.5 millimeter between the bottom of the cylinder and the mid plane of uh, the the plate. Okay, and I'm assuming that the cylinder is moving with an initial velocity of 40 meters per second. The dimensions are given here. The plate is made out of aluminum, but the impacting object is modeled as a steel. Now, it is, of course, possible to model this cylindrical object as a rigid body, uh, but I'm actually modeling it as a steel with the given properties. Now, the friction coefficient between the two uh, object is zero point 0.3 and I'm using general contact. Everything is taken as default and the total duration is 5 milliseconds. Okay. As I said, the boundary of this thing is all clamped. Now, when it comes to inputting the information, obviously Young's modulus and Poisson ratio and density, these are fairly straightforward. But I'm assuming that the material, the plate behaves plastically, therefore yield strength is 100 megapascal at zero plastic strain, that means yield strength. And then at 110 megapascal, the the strain, the plastic strain is 0.05, which means 5%. Okay. Now, this, of course, is I've done it many times, so it's fairly straightforward. Then you go and select the damage model. Okay, right here, the damage model. When you select the damage model, and you're going to use ductile damage, this window pops up, and the only number that I'm going to put in there is 0.001 for fracture strength, and these two I'll leave it as 0. I'm following the steps of the previous YouTuber. As I said, I'm not making any claims on the validity of these things, but now, in order to also show the damage, basically get rid of the elements and things like that. You also have to go to input the damage evolution, evolution parameter, damage evolution. So right here, you click on the damage evolution, and the only number that the YouTuber includes in there, the previous YouTuber including there, is the displacement at failure, which is zero 0.2 millimeters. Okay, using displacement, not energy, because here you can use two, and there are other options, but I'm just following, replicating the steps of that reference. Now, if you look at that YouTube video, you see that the windows are all different. Okay, for example, that damage evolution, there's a box here which says uh, sub option. What is that? Yeah, sub option right here, and then you put the displacement of failure over there, point two, uh, 0.2 millimeter. Completely different. Now, the plate is modeled with S4R, reduced integration, four-noded linear reduced integration, and the cylinder is modeled as eight-noded continuum element, break element, basically with reduced integration. So after I mesh it, because I'm doing explicit dynamics, I have to go and change this, because by default this is going to be S4. You have to go and change this thing to reduce integration. Okay, we'll do that. Now, also, in order to show elements disappear in front of your eyes, you have to request an output. And the main thing is that when you go to failure measure, you scroll down thing in the output request, you have to check this status option. Otherwise, the materials are not going to disappear while you're watching it. Okay? Good. So let's go ahead and do this. We are dealing with an assembly right there, and I'm going to insert my first part, which is going to be that plate, all right? And there are different ways of doing it, so I'll go this route. So insert a 3D part, and I'm going to call this thing plate. Okay, so right-click properties. I'm going to call this thing right in front of it. I put down plate. And instances also put plate in front of it. This is for bookkeeping purposes, and you don't have to do it. Okay, and now we're going to make it. So double click on the 3D shape. All right, and on the horizontal plane, I'm going to sketch a circle of radius. I believe I had it as 150 millimeters. So okay, so over there, 150. Okay, exit. Now I want to put a surface through that because it's a plate. So in order to do this, of course, I can't do it in part design. I can go to generative shape design. And there is a FILL, fill option. Already it's picked. So it's going to put a surface through it. Why don't we go ahead and do the material properties? So let's go ahead to tools. Let's create one. I'm going to call it aluminum, and today is October 12th. So, okay. By the way, this is done on the 3D Experience Release 2023X. So right there, you can see, wait, October 12, right? Let me check again. October right there, aluminum October 12. Apply. I can close this on that part. We apply that. Now we have to input the property. So double click. All right. Structures, general option, density, and there I have it as well. You can put in terms of kilogram per meter cube, but let me remind you that this unit was actually specified as right here, tons per millimeter cube. So it's up to you. You can either put it like this or put down 2,500 kilogram per meter cube. And that's what I'm going to do, okay? Actually, I'm going to put this thing. So it looks like I haven't changed my unit, so I'll put down 2,500 kilogram per meter cube. Okay, good. Now, then we're going to do the ABAQUS multiphysics, mechanical, elasticity, elastic, and the Young's modulus for the aluminum. I asked it to be 70,000. This is already MPa, so it's going to be 70,000 MPa. And Poisson ratio is 0.3. 0.3. Okay. Then you go to plasticity, metal plasticity, plastic, and put the numbers in there. So the yield strength was 100 at the zero plastic strain. And the second point, I'm using bilinear basically behavior. Although if you have the data, you can just put it in 110. And this is at 0.05. 0.05. Okay, takes care of this. And then you go to damage, scroll down. Here's damage, ductile material, ductile damage. Okay, so I have, based on that table that I showed you right here, it's fracture strength, strain, stress triaxiality, and strain rate. Notice that I've checked this thing, although I put 0 in it, probably we don't need it, but that's okay. So I'll use strain rate data. That's why now I have 3 columns here. This one was 0.001. This is a 0, and this is a 0. If you have to put these numbers, otherwise you won't take it. And then you go to, if you expand this thing, there is a ductile damage evolution. You click on it, and this is where you put that displacement at failure, which is 0.2 millimeter. 0.2 millimeter. Please keep in mind that once again, in order to understand what's going on, it's very easy to generate good-looking videos and color and things like that. You really have to find out what your material follows as far as the damage is concerned. So I'm just replicating the steps in that video, so therefore I'm not questioning it, and I just say okay. So that takes care of our aluminum. Go all the way to the top, all the way to insert our second part, which is that object, impacting object. So by the way, let's do a quick save here. And then we're going to go and insert, let's see, 3D part. I'm going to change this thing to steel, or I'll call it steel, yes, properties. Or why don't I call it the impactor? Impactor. Okay, same thing here. Impactor. Okay. Now you can make different. We can do it different ways. For example, as a separate part, you can actually go and make that thing and then position it properly. But the way I'm going to do that is I'm going to create a plane because I don't want to use the um, constraints and things like that to move things around. I'm going to make a plate here, which is 2.5 millimeter above that plane, and on it draw the circle and then pat it up. Okay, so right now we go to assembly design. Let's go to part design to make it. Okay, we can make a plane offset from that plane, a 2.5 millimeter. That was the gap, remember? 2.5 millimeter, and on it I will sketch. The radius of that impactor was, I think it was 20 millimeters, so 20 mm. And remember, I'm talking about radius right here, 20 mm, and a height of 80. Okay, we go over here, exit, and pad it. Now this is generative shape design. I cannot pad stuff here, so I'm going to switch to a part design. And under essentials, there's my pad, 80 millimeters. Good. And now we're going to apply a material to it. It's a fairly standard elastic problem. So let's go make it. Under tools, we're going to create a material. I'll call it steel. October 12. Steel October 12. Apply. Go through this. Put it on that part. Say OK. And now we just put down the number, density, material property, and Young's modulus. Double click on it. Structures, general option, density, and I believe the number that I have in there, in that slide was 7.85, 7,850 kilogram per meter cube. Okay, and then ABAQUS multiphysics, mechanical, elasticity, and this is 210. If you go to that slide, it says Young's modulus is for steel is 200 and actually I forgot to mention that, but it's going to be 210. Yeah, I'm not absolutely sure whether that video on ABAQUS CA is using 210 or using 200. I'll use 210. 210 gigapascal or 210,000. Okay, and Poisson ratio is 0.3. That's it. There's nothing else. There's no plasticity. You just leave it like that. Okay, so let's go do a quick save here. Okay, if you look there, there is a gap of 200 here 2.5 millimeter. Okay. Now remember, the shell thickness later on is going to be 3 millimeters, so the actual gap is not 2.5. The actual gap between the two pieces is 2.5 minus about 1 millimeter. Okay, good. So that takes care of this. Now we can go and create. Let's go all the way to the top. Now we're gonna create our mesh. Okay, so let's go to. There's two ways of doing it. You can either go all the way to the top, right click, insert, and insert FEA, finite element. You see, insert. Uh, I don't have that here. So let's go switch to structure model creation. We're going to do an empty FEA. Okay, good. And we're going to include both of these pieces in it. Both of these. Okay, right there. Good. So it's all the way on the top. Now we're going to mesh. Let's start with the shell mesh. So mesh, quad mesh, surface quad mesh. Is that right? Yeah, surface quad mesh. This size 5 millimeter. That's what I had. And mesh it linear. That's the mesh that we had there. You say okay. While we are at it, let's do the properties. Properties, shell section on this part. Thickness, I believe it was 3, if I'm not mistaken. Let's check it out. Uh, yeah, 3 millimeter thickness, right there. Okay. So we go back here and we say okay. All right. And now we're going to do the mesh the other piece, this piece. So we go to mesh. Now I just want to tell you that here it looks like the option you can use this one or hex dominated mesh. But when you do that, it also, or at least when I tried it, it also creates these uh, uh, elements which are tetrahedral. It's not supposed to, but or maybe it is because it's hex dominated. This one will do just entirely hex. Okay, so you click on the sweep 3D mesh, select this thing, linear, again 5 millimeter, number of layers. I put down 220. I don't exactly know what is it that YouTube video has, but I put down 20. There we are. Okay, good. Now, the kind of element that it generates, let's check it out. There is, oh, properties. I have to do the properties, by the way. Click on properties, solid section, select this piece. Material is properly selected. You say, okay, let's quickly save this. And see if we can check our element. See now on the meshing, mesh part manager. Uh, yeah, it shows you the kind of elements it's using, but it will be actually the kind that you want to switch later on to reduced. Okay. reduce integration. All right, so we're done here. We go all the way to the top, all the way to the top, and we're going to go to not the structural scenario creation because this doesn't have the explicit license, but this one, mechanical scenario creation. Remember, the ABAQUS can be done in either one of these. These have more licenses, this one does not. So medical scenario creation, not medical, mechanical scenario creation. Wait. Okay, so we want to do structural, although general will also work, but and the elements we already created right there. We say okay. Let's give it time. Good. Now we're going to go to procedure. It's explicit dynamics. Explicit dynamic step. Click on it. The total duration is 0.005. Everything else is default. We say okay. All right. Now we're going to do the boundary conditions and things like that. So let's go ahead to the boundary conditions and do a clamp on this entire outer edge. Let's see if it selects the edge. No, this is the face. I don't want the whole face. Cancel that. What I'm going to do is right click, visibility manager. Don't show me the mesh. I don't want to see the mesh. Okay. And I think this is the edge, right? Yeah. So now we're going to clamp it. Now, if that happens, that means that something is blocking it. So let me hide the sketch. Right click, hide the sketch. Actually, let's try it again. Let's go and do it differently. Let me go ahead, close that. I want to hide my, let's go here and hide that sketch. Part body, this is the sketch. See that? I'm going to hide this. Okay. Now let's go and try to clamp it. There. One edge, right there. And we say, okay, this is all clamped. This is all clamped except that it doesn't show me the boundary conditions. I'm not sure why. Analysis cases, this connections. Let's see now under FEA model. Boundary condition. Still doesn't show it to me. I'm not sure. It says they're shown, but I don't see them. Let's not worry about it. Let me see. Hide and show. Yeah, I'm not sure why it's not showing the icon for the clamp and things like that. Okay, so let's get rid of this. All right. What else do we want? Initial velocity. Okay. Initial velocity, initial condition, initial velocity. Now, in that video, the fellow is not using initial velocity, using predefined field, but I don't have that predefined field. You see that it's over there, but it won't let me take anything. So I'm using initial velocity, and on that entire part, on that entire, not the face, okay? So let me get rid of this, remove all. Let's go select the actual pad or part body right there. Not the entire the face, because that may cause a problem. Although it should not, but anyway, it is. So in the direction Z, negative 40 meters per second, which means negative 40,000 millimeters per second. Okay. I still don't like the fact that these symbols are not shown. There must be a reason, but that's not a big issue right now. And what else do we have here? Oh yeah, so interaction. First, let's create the friction coefficient between them. Contact property, friction, specify, and I believe I asked for 0.3, 0.3, okay. And let's give it a name, my friction, because this is just a name. Okay, so we say fine. All right, and then general contact. Make sure that you select the proper friction model, my friction, right? This is a frictionless, my friction. We say okay, everything's default. Let's do a quick save here. All right, and now we're gonna go and do the output request right here, output request. Okay, so what I'm doing, the step that I'm doing now is, oh yeah, I forgot to change the type of my elements. We'll do that in a second, okay? So I'm doing this first and then go back and change the type of my elements. We'll do that, okay? So under, let's get the stresses. I mean, whatever you want, strain, displacement, forces. Some of these are coming by default. By the way, evenly, let's see now, I'm using output request, evenly spaced time interval, and the time interval, the number of them is 50, okay? So time interval, the number of them is 50. But the important thing is you go down here under failure measures, scroll down, that status thing must be checked right there. We check this and we say okay, save everything. I'm not asking for any time data. Generally speaking, these explicit solvers, you have to go and actually make sure that there is artificial energy is low, etc. But anyway, I'm not doing that. Now, the other thing is that the material, remember the element type. So if you go back to, this structural, expand this thing, element type assignment, double click on that. Notice that the shell is S4. Let's change this to reduced integration, and this is already correct. Linear break with reduced integration. Let's do a quick save and run it. First check the model. No problem there. Then check the simulation. Make sure nothing obvious is missing. Okay. Just give it time to check it out. These may take a few extra minutes. These checks are going to may take a few extra minutes, but they're worth, because if there's anything obvious that's missing, uh, it's going to pop up. There are some warning messages, but that's okay. We just let it go. It's a good idea to read these warning messages. Okay, done. And now we're going to run. This is the run, simulate. It's going to be a quick run, probably maybe 1 or 2 minutes after you get the window, the dialog box, and say okay. It's going to take maybe 2 minutes at most. Okay. Yeah. So if you choose the iterations tab, wall clock is right here, as you know. This is the wall clock, the actual physical time. It says 9:19, so this thing is going to start. It goes very quickly. This is seconds, right? We are almost at the end. Yep, 61% done. This is supposed to go 0.005. Took 1 second, or 1 minute. Done. Okay, so let's actually close. Once this finishes, let's close this. See what happens on the side. So this is the initial situation. Then this is going to go down. Oh, see that? There's damage here. There we are. Okay, so I replicated the steps. I'm not claiming that there is accuracy involved here because we're not doing a mesh conversion study. We are not sure if this material actually behaves like what we are claiming, etc. So let's go ahead and create a video clip here, or actually animate it. That's what I mean. Okay. And remember, you can plot different things. This is the von Mises. You can plot the, let me stop this thing. You can plot the displacement. I mean, it's not very useful, but okay. And that's pretty much it. We'll do a few more of these, assuming that we have the proper damage. There are the different ways of different damage models, and this is one of the simpler ones. By the way, if you look at some other video segments from the ABAQUS CAE, you'll notice that they have to go and activate some switches in order to be able, not here in the ABAQUS CAE, activate in the older versions, older videos, activate certain switches so that we can actually see the thing piercing through. But gradually they fix those things, and it looks like, at least in the version that is buried inside of that inside of the 3D experience, release 2023X, those are taken care of. And yeah, you don't have to worry about it. Good luck. By the way, before I stop the video, I want to point out to something that I might have said, and I did say it. Remember, in the when I requested the output, which was this slide, I said that you should go there and ask for status. However, if you let me go ahead and that was output 3, right? Double click on it, and notice that this is the one that I sell. Oops, where is this? This is the one that I did select. But when you look at this, when you expand this thing, uh, hang in there. So we go here on the status. It says for some failure and plasticity models. So what I did is I went and unchecked that for the present plasticity model, which was ductile failure. I unchecked that, did not request it, and I ran the problem again, and you still could see that the impactor was piercing through the plate. It could be that some of those models. Let me say okay. Let's go to that material, aluminum right there. This is the one that we did, right? And under damage, there are different models. The one that we have is ductile damage. Okay, uh, but there are some of these other models that if you don't check that, then you may not get what you expect as far as the video is concerned. Okay, that's pretty much it. Now, bye.